Okay, free energy changes for non-standard states. The standard free energy change, very narrow set of conditions which you're almost never working with. Here, liquid water in its standard state, pure water in equilibrium with water in the gas state, that would have a pressure of 1 atmosphere. The free energy change for that is positive, 8.59 kilojoules per mole. So, this is positive. Should that process be spontaneous? No, it shouldn't. But is it? Actually, it is. If I spill water on the floor, is it going to evaporate? Yeah. Eventually, yeah. And like the sweat on my forehead, right? It eventually evaporates. Why does it happen? Because it's not at standard conditions. So standard conditions would be the partial pressure of water in the air around it being 1 atmosphere. But actually, under ordinary conditions, it's much, much, much less than 1 atmosphere. And so the reaction will be spontaneous. So we need to be able to calculate delta G without the degree symbol for non-standard conditions, because that's what we're almost always going to be using it for. So delta G without the degree symbol is change in free energy under non-standard conditions. And this is equal to the standard free energy under standard conditions plus RT times the natural log of Q. This is the same Q we saw before, the reaction quotient. The reaction quotient is calculated exactly the same way as an equilibrium constant. But the equilibrium constant uses values of concentrations or pressure at equilibrium. Q, you calculate with whatever it happens to be right now. Okay? T is the temperature in Kelvin. R is going to be this version of the ideal gas constant. You're also familiar with the 0.08206 liter atmospheres per mole Kelvin. Well, you want to use that one when you've got volumes in liters or pressures in atmospheres. But if you're dealing with energy, you want to use this one. If you've got reactions with gases, we're going to use Q pressure. We use their pressures. And for solutions, we're going to use QC with concentrations. Okay. So here we've got this guy right here. I really don't want to do this slide. We're not going to.
No.
I think they're marginally useful, those troughs with things rolling up and down. So, at 25 Celsius, normal temperature, liquid water is in equilibrium with water vapor at a pressure of 0.0313 atmospheres, because they told us these are the conditions. And these would be kind of normal conditions, right? And so our chemical equation here, the liquid to the gas, right? So if we're calculating Q, it's going to be, this is pressure, it's going to be the pressure of the H2O divided by, oh, that's a liquid. Liquids and solids don't get used, right? Because they don't change. So it's just the pressure. So Q is equal to the partial pressure of the water here. So delta G is this positive number. Look. The standard delta G is a positive number, is plus 8.59 kilojoules. and then we're going to add R times T times the natural log of Q. We do need to convert. See, this happens all over the place. This has joules in it because it's a very nice number at that unit, and joule is a base unit. So they're not going to change it just for that. So this is joules, this is kilojoules. So let's do this in kilojoules. So then this is 8.314 times 10 to the minus 3 kilojoules. So 8.59 plus 8.314 times 10 to the negative 3 times 298.15 times the natural log of 0.0313. Cool. That's in equilibrium. Q is supposed to be 0. Those are pretty small. Quick revisit to significant figures. 8.59, yes, 8.59, that's this guy. And then we're adding something here. Well, what is that something? 8.314 times 298.15 times the natural log, 0.0313. So, let's see, let's use some different colors here. So this part is negative 8.58696941 kilojoules. So I've got numbers with 4 and 5 sig figs. I also have a number with 3. So if we do that with 3, so what I'm doing here is I'm taking this number and I'm adding this negative number. And my calculator gives me 0.00303 and some other things. Where's the uncertain digit in the 8.59? It's the 9. This digit is uncertain. Where's the uncertain digit in this one? We could argue about it, but probably the same place, right? Here or here. Doesn't really matter because this one is the largest. So we cut off our number at that decimal place because there is uncertainty in that place. So we get 0.00 plus or minus 0.01. So it is 0 even though it doesn't look like 0. The first time I do this calculation every semester, I have this minor heart attack because I'm like, wait, it's supposed to be 0. And I have to remember, no, okay. So at equilibrium, delta G is equal to 0. That means the reaction is not spontaneous in either direction. Does that make sense? It's at equilibrium. Now, we know that it's a dynamic equilibrium, it's going back and forth, but overall, is there any change? No, it's not spontaneous in either direction. Questions? So for other non-standard conditions, you're just going to calculate Q and substitute it into the equation. This one's boring. I'm not going to do that one. Let's do this one. It's more interesting. So here we have this chemical reaction, 298K, calculate delta G. We're given the standard free energy change, and we're given the partial pressures of the gases, because these two are gases. The S is a solid, right? So we have to calculate Q. So Q, in terms of pressure, is going to be, that's a solid, so we're going to ignore that one. It's going to be this one, the gas, right? The partial pressure of H2O squared. That's where the 2 goes. Divided by the partial pressure of H2S. That also has a 2 coefficient, also gets squared. And SO2 is by itself, so this is partial pressure of SO2. That feel a little familiar? Cool. Okay, so I've got these values, I'm going to plug them in. Just be careful because they're easy to mix up. H2O 0.0100, it's going to be squared. H2S 2.00 squared. And the SO2 1.50. So Q's 1.67 times 10 to the negative 5. Delta G for the reaction is equal to the standard delta G plus RT natural log of Q. Delta G is minus 102 kilojoules. And then we've got R, 8.314. And guess what? It's going to be that kilojoule thing again. So let's just times 10 to the minus 3 kilojoules per mole Kelvin. Times the temperature, 298, times the natural log of 1.67 times 10 to the minus 5. That's a good question. No. I don't know what I did, but it's wrong. So I'm going to pretend I didn't do that and answer your question instead. So the question was, we've got pressures here in atmospheres. Shouldn't we use the R that has liter atmospheres in it? That's a very, very reasonable question. But we're calculating an energy. So this is kilojoules, And if we use liter atmospheres per mole Kelvin here, we're going to end up with a number of liter atmospheres. Because these atmospheres are not actually coming into this equation. The Q, when we calculate Q, these don't have units because they are in reference to a pressure of 1 atmosphere, and so all the units cancel out and go away. So we don't need to worry about them. Does that make sense? Okay, that's a great question. Now, what the heck did I do wrong? Oh, I multiplied instead of adding. That would do it. Change that to plus. Okay, that looks 129 point, well, minus 129. But that's still not what they got. I'm just gonna try it again. Yeah? What? You think the book's wrong? That's entirely possible. Oops. Well, that's nice. Now I got minus 117.8. Oh, good grief. Oh, no? Natural log of 1. Oh, I had the wrong exponent. It was 5. Okay. Yeah, I'm going to stick with that one. I think the book probably is wrong. Did anybody get minus 197? No. So I thought I had caught all of the places where the answers in the back of the book were wrong, but apparently I missed this one. Any questions?